So it's a privilege today for me to be able to welcome today's speaker, Professor Monica Grady. She is the Professor of Planetary and Space Science at the Open University and is widely known for her work particularly on meteorites. She did her first degree in Durham and then a PhD here in Cambridge on carbon in stony meteorites. And it's that area of meteorites where she has an international reputation. She even has an asteroid named after her, so I'm told. Her enthusiasm for research, I think, was evident to everybody. She was involved in the Rosetta spacecraft and the Philae lander, and I'm doubtless have seen Monica's enthusiasm on the television, the pure pleasure and the relief when that landed successfully. So it's a pleasure to welcome Monica Grady here to us today, and she's going to speak on comets and asteroids, moon and Mars, science and faith, and life and death. Thank you.
Thank you very much for the invitation to come here, and thank you for coming to listen. I hope I don't, let's put my timer on, I hope I don't disappoint. I seem to miss the death off the end there, which I think is possibly a good thing. So I wasn't sure how I was going to structure this talk, so we'll just swing it and see how it goes. So you've already heard my background there and what I'm doing at the moment, which is being Professor of Planetary and Space Sciences at the Open University. And as part of that, my teaching commitments are I do contribute to a general science course in which there is a module on planetary formation, origin of life. I teach in our second year chemistry curriculum, and I teach a module which includes talking of the origin of life. And I'm also now involved in a master's degree in terms of spaceflight instrumentation, which is building instruments to go and look for life on Mars. So that's what I'm doing for my teaching. So my research interests are, as I say, is in the origin of the solar system, the origin of planetary systems around other stars. Particularly I'm interested in Mars, how the evolution of Mars, and also in whether there's life on Mars, and also the possibilities of life beyond the Earth. So how do these meld with my personal life, where I am a practicing Catholic? You know, I'm not a terribly good one, but you know, if you practice enough, you maybe get better. I am a catechetist for 6 to 7-year-olds, so I teach 6 to 7-year-olds about the Catholic faith, and I help with confirmation classes for 12 and 13-year-olds, and I'm a Eucharistic minister. So it's like I do have a very deep and sincere Catholic faith. So how do I bring those two sides of my life together? Usually by ignoring one or the other. Which is like, okay, so I'm in church on Sunday and I believe in the virgin birth, and it's like, right, okay, do I? Please don't question me on that one. And it's just it is difficult in many ways to bring the two together. So I'm going to talk really about the two ways I think of things in the two sides of my brain. And you can then conclude whether I have managed to actually accomplish some beautiful complementary lifestyle which allows me to believe in two different things simultaneously, or not. And I'm going to take two subject areas, which one of which I am very interested in, but I cannot talk with any authority on, and that is the origin of the universe. And then the other thing which I'm also very, very involved in and interested in, and certain parts of which I can talk with authority, but only very, very small parts. And then bring these together to see, if we can talk about faith and science and religion together. So my background then as a planetary scientist, this is possibly this I'm afraid is probably the only bit we'll talk about asteroids and comets and stuff. So My background in chemistry and geology has brought me to planetary sciences, which is a mixture of physics and chemistry and geology and biology and all sorts of things. So all facets of subject area. And we start with the premise, or I start in my premise, that the sun was formed from a cloud of gas and dust, mainly hydrogen, very turbulent fragment of a molecular cloud. And the solar system, the sun and our planets, was born 4,567 million years ago. Now this is a very, very easy number to remember. And it's what, when I talk to schools, I say there's only one fact I want you to take away from here. One number, 4,567 million. Nice and easy. That's how old the solar system is. Now there are stars in the Milky Way that are older than our sun, and there are stars in the Milky Way that are younger than our sun. But so, you know, that's how we look back to fragments of the molecular cloud which have become embedded, mixed in with meteorites. So we can study meteorites, which are chunks of asteroids, to look at what has gone before the solar system came into being. Because the star, the sun, was not born in isolation. It was born from a molecular cloud, and there were many, many other stars within that molecular cloud, some of which were already old and coming to the end of their lifetime at the time our star was being produced. And all stars have a stellar wind, and entrained in that wind are particles that come from those stars. And so winds from different stars, at least 35 different stars, have contributed particles to the dust from which our planetary system formed. So we have within our planetary system, I don't know if you can see down here, we've got the sun, we've got the planets, we've got the asteroid belt, which is between Mars and Jupiter. We have another belt here beyond Neptune, which is called the Kuiper belt, and Pluto, which was recently demoted from being a planet, has now been promoted to one of the largest of Kuiper belt objects, which I think is a really good career move for Pluto. You know, it's gone from being the last and smallest planet that we haven't bothered to go and see before. It's gone to being the first Kuiper belt object that we've had the opportunity to explore, and I think that's really good. So we've got Pluto down here, and hundreds of thousands of other Kuiper belt objects. They're made of rock and ice. The asteroids are made of rock and metal. And then going beyond here to the very outermost edge of our solar system, we have something called the Oort cloud, which we don't know, nobody's seen it. It's called, they describe it as a hypothetical construct. But, you know, from what we know about comets, this reservoir of all the comets, with most of the water and ice from the solar system, has to be in this icy shell which surrounds the whole of our planetary system. So we're looking, when I look at asteroids, this is an asteroid, as opposed to this up here, this is Comet 67P, Churyumov-Gerasimenko, the target of the Rosetta and Philae missions. So when we compare asteroids and comets, we're looking at objects which formed 4, 5, 6, 7 million years ago. And some of them have been very heavily changed, processed, heated. Some of them haven't. The planets, so we have Mars, and then we have the satellites of the planets like the Moon. A lot of them have been, so the planets have melted. So like the Earth has got a core, Mars used to have a core, it's called differentiated, so it's got a metal core and a rocky crust. And that tells us different things. Now Mars is very, very like the Earth. I mean, okay, it's got no atmosphere, it's got no water, it's got no life, it's got no volcanoes, but apart from those minor things, it's very, very like the Earth. So it's an obvious place to go and look for life, and I will come back to that later on. But this is my background, this is what I study. I look at rocks from the asteroid belt, I take data from telescopes and from spacecraft, space missions, and try and put together a picture of how our solar system has evolved. Now that feeds into how planetary systems around other stars have evolved. Now then there is a massive jump from there to the Big Bang. All right, in fact there's a gulf so wide that the cosmologists who study the origin of the universe via the Big Bang, they regard us as very, very parochial, whereas we regard cosmologists as, well, charlatans is probably too strong. That's very, very unfair, very unfair. Right, so I've just got, to get us back onto the faith side of things, I thought, oh well, I'd better prove my erudition by showing some quotations from people. And so this isn't the most recent, this is from October 2014. And Pope Francis, he's like a good man, is Pope Francis. Do you see him with the Mexican hat on a couple of weeks ago? It's like he's a good man. So he's saying that scientific theories are not incompatible with the existence of a creator. Actually, they require it. So, you think, well, the Pope would say that, wouldn't he? He's not going to come out and say, well, actually, we don't need a creator. But there you go. But where's the next one? John Paul II, he really, really did set the ball rolling as far as, let's start talking about this, distinction between science and religion, which has built up and built up and built up over the years. Going back 500-600 years ago, there was no distinction between science and theology. It's like people studied things, and they studied science and theology. It wasn't until you started some of the great experimentalists starting to prove, trying to understand rather than just accepting, that there started to become this division. But if you read, this is the preface to a book of papers at a conference which John Paul II called. The conference was in 1987, and the book of papers that has come from it is in 1988, and you can get at it on the web. And this is just one little quotation I've taken from it. To be more specific, both religion and science must preserve their autonomy and their distinctiveness. Religion is not founded on science, nor is science an extension of religion. And I think that's very important. When people, well, I don't know, love him or hate him, Richard Dawkins, discuss. He's so dogmatic about scientists, cannot, should not, must not believe, have any faith, that there is no evidence whatsoever for a God. I think he's confused. Each should possess its own principles, its pattern of procedures, its diversities of interpretation, and its own conclusions. And if you can look at scientific things, look and prove, all right. So I've got here comparisons between St. Augustine and Stephen Hawking. Two great men in their different ways. The universe was not created in time, but with time. Even Stephen Hawking says there's no precise moment when the universe began, because there is no precise moment when time began. And so immediately you start thinking, oh right, okay, so this Big Bang then, does it need a creator? Well, I don't know, I'm not qualified at all. And then this famous quotation from Galileo: the intention of the Holy Spirit is to teach us how one goes to heaven, not how the heavens go, which is, a beautiful, beautiful phrase. Okay, so, oops, did I go through two then? No. I did, yes. So, if we compare what I do in my daily life, I apply the scientific method to the problem. So, I ask a question. My question might be, how did the universe begin? Well, how did life originate? It is more likely to be, why is the electron microscope broken again? But that's the sort of, I'm not answering big questions like this on a daily basis. Those frontiers of science, I leave them unpushed back. So, but I ask a question. My question might be, I've got this piece of rock that's come from Mars, I want to analyse the carbon that's in it and find out whether that carbon is organic, and then infer from that whether the organic carbon is biological or non-biological. So I have to design an experiment to help answer that question. I get some results, I have to interpret them, draw conclusions from the results, and I have to then take those results, make some predictions from those results as to what the next experiment will show. And then I have to keep going until I am satisfied. I have to make sure that my experiment is reproducible, repeatable, that I have accounted for any strange effects, experimental artifacts. I have to make sure that, you know, my statistics are kosher, and I have to be able to make a prediction which is testable. And that's the scientific method. All right, and so I'm good for that, except on Sundays, when I might want to ask a question, where did the world come from? And then I make up a story, you know, to answer the question. And Adam and Eve, you know, the world was made in 7 days or 6 days, using imagery. And then you have a mythology that grows up around those answers. And people believe in different things in different ways at different times. And that's one of the big differences, and that's one of the big places where arguments and divisions start. So, case study 1, the origin of the universe. Okay, so we can say, right, you know, we've got something called the Big Bang, which is a singularity. It was a point of infinite density, and in a fraction, tiny fraction of an instant, suddenly there was a universe. Okay, it had expanded. It had started to cool from incandescently hot. It was particles. Well, they weren't in particles. They were subparticles, which then, as the singularity continued to expand and cool, these particles came together. Eventually, they formed hydrogen, which eventually started to form stars. Some of the stars got hot enough to switch on with nuclear fusion, and they started to burn. And then at that stage, it's like, you know, let there be light. Okay, so we now can see what's going on. But there is a point beyond which, or before which, we cannot see. We cannot make any measurements. We cannot go far enough back in time. And then you start to get the arguments, well, what happened before the Big Bang? And the first time I asked that question of one of my physicist colleagues at the OU, he gave me an answer which I was not satisfied with, and I'm still not satisfied with. He said, you can't ask that question. And I said, well, I can ask that question. He said, no, you can't ask that question. You can't ask the question, what happened before the Big Bang? Because there was no before the Big Bang, because time began at the Big Bang. And I was like, yeah, but what was there before time? And it's just like, he just sighed and said, stick to meteorites, which basically meant he didn't know the answer. Okay, so fair enough, right? So it's like, okay, so, you know, things going, and we've found gravitational waves. We've got a new window on the universe. I know this because I heard it many times last week. We have a new window on the universe using gravitational waves. It's like, wow, that's fantastic. I don't know how we're going to use them, but, you know, there's going to be a new type of spectrum, not based on electromagnetic radiation, but based on gravitation, and you know, everybody's so excited about this that I feel I ought to be excited too. Well, I am, because we've been looking for them for a long time, and, you know, it's justified Einstein's existence. So we've learned so much. And I know I've got at least 2 astronomy colleagues in the audience, and I know they won't be offended when I say this. Astronomers always want bigger telescopes. They want bigger telescopes. A telescope is something which collects radiation. It might be light, it might be X-rays, it might be radio waves, but they want something to collect more of it in a shorter time, so that they can see further and further back in time. And it's like you're going to get to a stage when we can't see that far back. And that's when we're starting to think that, right, gravitational waves might really be able to help us go further, go beyond what electromagnetic radiation can help us do. So we've got lots of predictions that come from the Big Bang model. You know, and Einstein, you know, he predicted gravitational waves. I'm not sure they come directly from the Big Bang, but he predicted gravitational waves. The Big Bang hypothesis has predicted all sorts of things. It predicted the effects of nuclear synthesis, and now we can measure these effects and we can see them. And the Big Bang hypothesis, theory, whatever, is the best we've got. Now, just up the road from here, Fred Hoyle was a great non-believer. He kind of turned Big Bang. You know, it's just as if something went bang. You know, in a derogatory term, because he didn't think that this was the right explanation. But at the moment, the predictions that this model make seem to be the right sort of predictions. On the other hand, you can say, okay, well, we don't know, we don't understand how the universe, how our star, how our planet got going. So we have to invent some way, we have to invent some thought of what it is. And so we have many different mythologies for the origin of the universe. From Hindu mythologies, from this is Viking, Yggdrasil, you know, and here we have, you know, the creator God saying, let there be light. And so we've got all these different mythologies which different people of different races and creeds subscribe to in terms of trying to explain. They know there's a universe here. They believe at some stage there wasn't a universe. How did that universe come into being? And these explanations, in some people's mind, are as rational as thinking that, well, something just went bang. You know, and it's like, well, what? Why not? The next, is this left or right-handed?
This right.
The other case study is the origin of life, the origin of humanity. Now, the theory of evolution, it still goes by the name theory. It's as much as an established fact as we can get to at the moment. We started off with physics. We started off with atoms, and the physics, those atoms react together and form molecules, and that's chemistry. And then those molecules, in the right sort of environment, reacted with each other in the presence of a catalyst, in the presence of the right sort of aqueous medium. They built bigger and bigger molecules. They had hydrophilic and hydrophobic ends, they bent in on themselves, they reacted with themselves, and somehow, wow, there's DNA. Some amazingly complex. Was it purely reactions? Did it require a lightning strike? Did it require energy from hydrothermal vents under the sea? Were the first organisms photosynthetic? Were the first organisms ones who use chemisynthesis, so energy from chemical reactions? You know, there's arguments backwards and forwards for both of those. What we do know is that after about 1 billion years, so the Earth had been going for about 1 billion years, we've got the first traces of microbial life. And then between about 3.5 and about 3.5 billion and 500, so 3 billion years, another 3 billion years, not very much seems to have happened at all. And then 500 million years ago, something called the Cambrian explosion, and suddenly a huge diversification of organisms. Enormous, you know, you've got all soft-bodied creatures in the bottom of the sea, you've got them then forming shells, moving onto the land, and then gradually legs, and then wings, and you've got this huge then diversity of organisms, all coming from something called the last common ancestor. All right, so there must have been, if you trace everything back, there must have been one thing that they all came from on the basis of the RNA that is extracted from these organisms. And there are 3 great kingdoms, 2 kingdoms of single-celled microorganisms and a big kingdom of multicellular organisms, more complex, and the distance along these twigs, if you like, shows how close things are to each other. And it's always good to point out that here we have animals, plants, and fungi, very, very close. You know, I think we share 60% of our genome with bananas, something like that. I read that somewhere. You know, so you don't diss on bananas, so it's good fruit. You know, so but eventually we became Homo erectus, and now we're Homo squatting at the computer terminal. You know, so that's like taking us into another sort of area as to, well, what's going to happen next. So that's approximately scientific explanation of where people came from. We've got this. Oh, he's got a navel. You know, oh, the Victorians who talked about that. You know, your navel comes from your umbilical cord, and umbilical cord implies that Adam had a mother. That here he is, you know, being given life by God. You know, on the Sistine Chapel. So it's like, Adam didn't have a navel. Did Eve? You know, these are the sort of things that you can spend hours in a bar discussing, I'm sure, if you're philosophers. You know, scientists, it's like, I'm not sure. But there is, you know, the Adam and Eve story, and it is it's a mythology built up from people who didn't know where people came from. And my feeling is, right, you go back there, Adam and Eve, and they had Cain and Abel, 2 boys. Well, it should stop there then, really, shouldn't it? I mean, you know, you're not going to make much progress. You know, so there must have been something else. But you know, this could have been, you know, the last common ancestor. You know, think of it in that sort of terms. There is a parallel. So faith then, what do we have faith in? All right, if we're religious, we might have faith in miracles, the wedding feast at Cana, the feeding of the 5,000, the transfiguration. These are some of the miracles of Jesus. Why would we search for a rational explanation for those miracles? The wedding feast at Cana, he took water and he turned it into wine. He took H2O and he turned it into ethanol, CH, whatever it is. It's got carbon in it, water hasn't. Oh, well, maybe he got the carbon from the pots. You know, maybe, you know, no! It's like you either believe this or you don't. There is no point in trying to explain it because you can't. If you could explain it, it wouldn't be a miracle. And you either think, right, okay, this is simply an expression of showing that Jesus had this power, this influence, that he was this important person, that he was encapsulating, embodying the spirit of love and fellowship and, you know, let's, you know, try and be better people. You know, you don't have to explain how that water became wine, or maybe it was mass hysteria, you know, that sort of thing. Similarly with your, you know, your loaves and fish. You'd have to take an ultramicrotome to slice those pieces of bread so thinly if you were going to feed 5,000 people. Now then, here we've got some more faith that we're going to be, you know, that you can think about. This is the Atlas experiment, which you can't see now. It's buried in the bottom of a 27-kilometre tunnel circle under Switzerland and France. It's part of the Large Hadron Collider. And it's one of the experiments which is taking these super fast particles, watching them collide and then measuring the things that come off. All right, and wow, they've found a Higgs boson. Whoa, you know, how excited are we about that? It's like, can you see it? Has it changed your life? No, but it has helped try and understand some of the really knotty problems of how atoms themselves are formed and built up, and interactions between atoms, and what happens with electrons, and trying to understand, you know, you start going on from here to things, marvellous things called quantum entanglements, and I've got no idea what, you know, how this works, but it's going to bring us quantum computing, and it's going to change the world, you know, maybe. But so that's, you know, that's from particle physics. From astronomy, this is a picture from the Hubble Space Telescope where it pointed the telescope in one particular region of the sky for many hours, many nights, to collect light from that just one spot. And each of these blobs in here is a galaxy. So each of those has got 100,000 stars in it. No, more than that. A lot of stars anyway. About 10 to the 11 stars in it. And there's hundreds and hundreds and hundreds of them. And that's just in one tiny little fraction of the universe. And it's not even a special bit of the universe. You know, the Hubble Space Telescope could have pointed there or there or there, and it would have seen the same thing. There are billions and billions and billions of galaxies in our universe, and each of those galaxies has got billions of stars in it. And when you think of that, and you think there are more stars in the sky than there are grains of sand on the beach. Now, that's a saying. I can't remember who said it, and I don't know whether they've got any statistics to back it up. But, you know, it's pretty impressive, because there's a lot of grains of sand on the Earth. But there are a lot of stars in the sky. This is a black smoker from the ocean floor. We didn't know about these until about 40 or so years ago. There was an assumption that because the deep ocean was dark, there was nothing living down there. Because we all know that the base of the food chain is a plant. Cows eat grass, we eat cows. Okay, it's simple as that. Unless you're a vegetarian and you go straight to the grass. But you've got to have the grass, you've got to have the photosynthetic organism, because animals cannot photosynthesize, animals cannot make their own energy. They have to use another food source. And no matter how elaborate your food web is, you know, it's like you have an animal that, you know, eats a bird, and the bird eats a fly, and the fly eats a maggot, and whatever. Eventually, it will come back to a plant. So it was always assumed that all the food chains, all the food webs were based on photosynthesis, harvesting light to generate energy. And then these black smokers were found at the bottom of the deepest, darkest oceans, Pacific Ocean. No light penetrates down there. What you've got is you've got a weakness, you've got a spreading centre where two ocean plates are moving away from each other, and there's a thinner crust, and heat from the molten crust, a molten mantle underneath, comes up, and it's superheated. And there's a chemical reaction between the superheated water and the cold bottom ocean water. And that reaction causes sulfur, which is in the bottom, which is coming through from the volcanic spring, if you like, to precipitate out as a sulfide. So you get a chemical reaction which makes sulfides, and that's what these are. So they're big chimneys made of sulfide minerals. And so at the top of them, you're getting this black smoke, and what it is, it's superheated water with these flakes of sulfide grains in them. Now, the reaction which produces the sulfides also produces energy, a chemical energy, and that energy is harvested by microorganisms, by bacteria and archaea who live at the base of these hydrothermal vents. And they are the base of a food chain, because there are tube worms and spider crabs and all sorts of very pale looking organisms, all fauna, all animals of some description, not plants, down at the bottom of this. So there's no light which penetrates down. There is some requirement for photosynthesis, because you need oxygen, and that has recycled through because of oxygen coming from the atmosphere, and that does require photosynthesis. So it's not a purely standalone mechanism, but it is the basis of a great chain, which we didn't know about until relatively recently. So until relatively recently, photosynthesis, that was it. Now we know there's something else, there's another explanation. So this is my summary, but I've got another 4 or 5 slides after that, so, you know, I'm not finished yet. So science and faith both relates ideas in terms of pictures, using imagery to get a meaning across. You know, whether it's a picture of a hydrothermal vent, or a picture of Adam, whatever. But this is the big thing. Scientific ideas can be tested, while religious tenets require faith. All right, and that's hugely where the two have to diverge. You know, they can diverge, but they don't have to be at loggerheads, because science can only take us so far. But it doesn't take us to why. Why did it happen? Why was there a Big Bang? Now, why isn't because, something went bang. That's a how. Why? Why did these single-celled organisms eventually build up? And that's okay, yeah, that's chemistry, that's biology. Where did consciousness come from? Where did free will? Where did self-motivation? All those things that it's like, that's neuroscience and is way, way, way above my pay grade. But there are things that neither science nor faith can help us with. And this is where you get questions. How can there be a God who allows war? How can there be a God who allows poverty, cruelty? My answer to that is God doesn't allow that. People allow that. We're the people who start wars and are cruel to each other and don't fight poverty. And it's like, well, how can God let you do that then? And it's like, well, we're not controlled by God. She's got far more better things to do than life. So, two discussion things that I just want to sort of lay before you are, we've got the Big Bang and the expanding universe, but there are all these questions, and then there's what is the universe expanding into? Oh, well, it's a rubber sheet, and it had, it warped where there were big things like black holes. But actually now we can see that the gravitational waves are pushing this around. And it's like, right, okay, but I still don't know what it's expanding into. Well, it's not expanding into anything, because as it expands, it creates space. It's like, that's just too difficult for me. That's possibly even more difficult than what was there before it. Mm-hmm. But what happens next? Is this going to continue expanding forever, or is it going to reach some limit, no idea what it is, and then suddenly contract back again? And then when it contracts back, is it going to then start expanding again? Have we got this sort of, breathing? Oh, maybe it's breathing. Oh, maybe it's a super being that's breathing, where it's inhaling and exhaling. I don't know. I mean, there are cosmological tests which, if it's something, it's 0 plus or minus 1, and if it's, plus 1, it's doing this, if it's minus 1, it's doing that, and, well, we're not quite sure what it is, but I'm sure if we had a bigger telescope, we'd be able to find out. Are we the only universe? I'm sure you must have been to some of Martin Rees's talks, or listened to him on the radio, or read some of his books. He's been talking recently about the multiverse. And he uses an analogy of water in a kettle, bubbles of steam that you see. It's like those bubbles, do they impinge on each other? What would happen if two of those bubbles collided? Are we lots of different multiverses? Now, to me, that's expanding the problem in a marvellous way. I was going to keep Martin occupied for years, and the rest of us too. But, are we the only universe? How would we test that? Can we talk to anything in another universe? I don't know. Evolution then. The origin of humanity. What turned the chemicals into biology? All right, so I said, you've got simple molecules like carbon monoxide and ammonia, hydrogen, and suddenly, we had DNA. It's like, right, okay, well, there were, and the biochemists can track, they can trace the pathways. But, this question again, when did an organism become conscious, sentient, tool makers, that sort of thing? You can start to look at them through the fossil record, back through the biological record. But the whole pathway, I don't think is fully clear. And then what happens next? Has evolution finished? Are we perfect? If you have the faith, humans were made in the image and likeness of God. That's what it says in the Bible. So we're perfect. All right? We're finished. we are not going to evolve anymore. So you can say, right, well, we believe in evolution, there were single-celled organisms, and now there's us, and we're the finished product. Alternatively, you can say, right, evolution goes forward to adapt to changing environments. So it's like suddenly something changes, it gets hotter, it gets colder, there's an ice age, people grow fur, whatever. Survival of the fittest, or however it is described. But we are not adapting to our environment. We now are capable of changing our environment and adapting it to us. So if it's too cold, we don't grow extra fur, we put a jumper on. If it's, we don't go hungry. Some do go hungry, but there is enough food in the world for all of us. We are destroying the world through climate change, through overuse of natural resources. So we are, in effect, not evolving, but destroying the environment. And you can start thinking things like, well, actually we know a lot more about the brain, we know a lot more about computer networks. People are applying the same algorithms to study neural networks and computer networks, and you can start thinking about the human-machine interface and robotics and all that sort of stuff, and it's like, well, maybe that's the next evolutionary sequence. Maybe we go from carbon-based to silicon-based. And we're thinking, well, maybe, who knows? So, I'm fairly certain this is my last slide, yes it is, and which is bringing me to life. And why is life so special? Why have we got a room full of people who are capable of thinking about life and about life's origins? Microbial life can arise wherever the conditions exist. Should be able to. We can see it on the Earth. Every corner that is habitable tends to be inhabited. Hot, cold, salty, alkaline, acidic, high pressure, high radiation dosage. There are simple organisms, single-celled organisms there, and some of them have got slightly more complex organisms, so they're all there. So there are plenty of places on the Earth where microbial life has got going and is flourishing. If you look at the solar system, there are plenty of places, including Mars, including Europa, including Enceladus and Ganymede and some of the other the satellites of Jupiter and Saturn. There are places. We know a lot more about Ceres, the biggest asteroid now, and some of the conditions below the surface of asteroids. So we can look and we can see there are many, many places within the solar system where all the conditions, the ingredients, the environment, it was all ready to go. No evidence so far that there's any there. There's no evidence for complex organisms, none. No kangaroos hopping across the vast plains of Mars. Not that anybody's told us anyway. So we haven't yet been able to find life anywhere else. However, we shouldn't think of being, that actually, if there is some form of life somewhere else, that it's naturally going to evolve to be like us. Because, think 65 million years ago, the dinosaurs, the dominant species on the Earth's surface, were wiped out by the strike of an asteroid 10 kilometres across. It changed the environment, the changing environment, heat, acid rain, all those sort of things. The dinosaurs could not adapt sufficiently quickly to that hugely quick, fast change in environment. But animals that could burrow, animals that could survive under the water survived. So mammals, little furry things survived, turtles survived, because crocodiles survived, because they could escape from those environmental changes. So a chance has brought humans to the head of the queue, if you like. So that might not happen somewhere else. And the anthropic principle. The universe is finely tuned for humanity. If the electron were a bit heavier, if the sun were a bit hotter, if gravity was a bit different, we would not survive. And so the anthropic principle says the universe is fine-tuned for us, so therefore life can't exist anywhere else. I don't agree with this at all. The universe is fine-tuned for us, but we actually evolved to deal with those conditions. It was the conditions were first, and we have adapted to them, not the other way around. That's my feeling. So that's all I want to say. I've sidestepped all the questions about the virgin birth. I am a person of faith. I am a person of science. I am quite comfortable with talking about my faith, and I'm very comfortable with talking about my science. I don't often get the opportunity to wax as lyrical as this to an audience, so I'm very, very grateful for that. I don't know whether I've got any conclusions, other than there is still so much to find out. And there are so many opportunities for us, and this is where I'm going to get pious. There are so many opportunities for us to worship what we can see around us, the daffodils, the sunshine, to recognise beauty where we see it. And that to me is one of the most important things, is to recognise the beauty. And if it isn't beautiful, then try and find out why and try and do something about it. Thank you very much.
Thank you very much for a very wide-ranging and engaging talk. I'm sure this raised some questions there, and I'm sure people have got plenty of other ones. So over to you. Who would like to start? Victor, I cut you off last time, so I give you the first one at the back.
Thanks for that magnificent piece. Two questions. How do you distinguish between the biological and the organic?
Right, okay.
That's the first question.
Yeah.
And the second one, very quickly. What do you think of life on other planets different from life as we know it?
Right, okay, well, organic and biological is very simple. Organic simply means it's got carbon in it. And carbon bonded to carbon, making big molecules. And so there are big molecules based on carbon up in the interstellar medium that have got nothing to do with biology. They have been made simply by chemical processes. Biology is something that involves an organism, which is, it's going through some type of energy transfer process. So organic chemicals are just chemicals. It just happens that life is based on organic chemistry. So that's one thing. What do I think about life on other planets? Well, I firmly believe that it should be there, but we haven't found any yet. I think the chances of it being on planets around other stars is as good, if not better, than finding it in our own planetary system, because there is such a wide variety of adaptations that organisms can make that I find it hard to believe that if you've got a simple physics goes to chemistry process, that the chemistry going to biology, which is the next logical process, I just find it very difficult to believe that it won't have happened somewhere else.
Your question just here in the middle.
Well, thank you.
Wait for the microphone's coming, so here we are.
Oh, thank you. Thank you very much. That was great. I think two things. One is, don't think we were made in the image of God. I think that God is made in the image of us, and that's why the conflict happens. But in support of poor old Richard Dawkins, I think the reason he's so emotional about religion is that he can see so many conflicts in the world that seem to be started, made by religion.
Yeah.
So I'm sure that's the reason for him being so adamant about it.
Yeah, I'm sure you're absolutely right. But the problem is that it's the weakness of people that leads to those divisions.
Sadly. Thank you.
Just straight behind you.
I just said actually men.
Yes, the weakness
It's
of
never
men.
women. It's not men.
Let's take a question there.
So, is God evolving?
Oh, difficult one. No, I think God is perfect. Is our mantra, and if we thought that God were evolving, what would be the end point of where God is going to, and what would God be evolving in reaction to? So it's not like God, as far as I'm aware, is not, sitting in a park somewhere being rained on and thinking, oh, I need to evolve to have a waterproof skin. So God, I don't think God evolves. In as much as I've never thought about it before. That's a very, very interesting question. Do you think God evolves?
I'm just wondering, you did, I think, touch, Monica, on the fact that there is a oneness principle somewhere, which we struggle to understand, but we're sensitive to, and that the longing for oneness and the longing for completion might be what this gentleman was touching on with regard to Dawkins. The two lads have a lot in common. And so is there something that's way beyond our understanding which is drawing us to express perfect love in oneness, which is deep in the heart of so many of the mystical traditions?
Yes, I think so. And I think that is part of where we're constantly striving. Everybody's striving. No matter what field, no matter what qualifications, no matter what background, people are always striving. They might be striving to generate their next meal, they might be striving to win a Nobel Prize, but everybody is striving for some sort of end point. And I think if you get to a stage where you can sit back and think, well, actually my life's comfortable, now what am I going to do? And you're bored, and it's like, it's dull. It's like, right, okay. I think everybody has to have it in them to be striving for something, and we can say that something is perfection. We believe now that heaven, perfection, is being in the presence of God. Now, it's just like, okay, right, fine, that's jolly good. I still don't know whether I can, understand that at all. But that's okay, I don't have to understand it. I'll understand it when I'm dead. And I'll come back and tell you about it.
Another question to gentleman there, and then in front. And I'm conscious we're over this side. So
Yeah. Could I just ask you something? You mentioned an Oort cloud. Is that
Yeah.
O-R-T?
No, it's OORT, after Yang
So is there just room for a moment to engage on that?
Right, okay, well, it's, like I say, it's a hypothesis. Nobody's ever seen it because it defines the edge of our planetary system. And so there's an assumption that the next star along, its edge is defined by an Oort cloud. And this is where the comets that were formed from ice, so they were formed, some of the last formed materials, as the temperature dropped, as the sun got going. They formed way out from the sun, beyond the snow line, and then interactions and movement of the planets pushed them out way to the edges, as far as the gravitational attraction of the sun stretches. So they define, if you like, the boundary of the sun's gravitational attraction. And so they are the edge of our planetary system. And so it's thought there are zillions of bodies of ice out there. And occasionally, there is maybe turbulence from movement from another star, and a shower of them come to the inner part of the solar system, where they get caught by Jupiter and become short period comets.
Can you mention a possible boundary?
Sorry, say again?
Can you mention a possible boundary?
Oh, it's about 100,000 astronomical units. Just like that. Approx.
It's like 4, 5, 6, 7. Just the odd bit.
Yeah.
but we do think that some things come from the Oort cloud eventually to come
Well, they come in.
causality?
They come in as comets. We don't think we've got anything that there's nothing of a hugely rocky, just rock out in the Oort cloud. So we don't think that asteroids have been in the Oort cloud. We think the asteroids are purely in a solar system.
Okay. There's another question there.
Oh yes, thank you so much for your lovely talk.
Thank you.
You said that scientists can't answer the why question. Why have we evolved in the way that they have described? But they could answer that, or the evolutionary scientists could, because they could say random processes have simply contributed to it. And the fact that we've thrown up an organism that's capable of contemplating its own navel or Adam's navel is pure chance. There is no why. So there is no distinction there. And the people who, faith people or whoever else, want to discuss anything other are like the old scholastic philosophers who are simply answering questions because they can, not because it actually means anything.
So in that case, if it's completely series of random chances, why did those random chances happen is what somebody would come back to you and say, you know, why that series of random chances, not this series of random chances. But also, the random chance is the how, in as much as the why. So it got going, you know, how did it get going? It got going by a sequence of random chances. Why did it get going? The why implies a purpose. And that's the difficult thing, is there a purpose to life? And you might think, probably not. No, actually, we are the product of a sequence of random chances. And there is no reason why we're here, and nobody will be sorry when we go. But I think that, I guess from a humanist point of view, you can still think, yeah, well, you know, you can make your mark while you're here. You know, humanity can make its mark, it can do good things. You don't have to have that creator urge behind you. And yeah, I mean, it's a really, really good point for discussion. Thank you.
Can I ask a question about the chemical composition of meteorites?
Sure.
As a biochemist, how sophisticated are the molecules you can find on that?
Oh, well, some subgroups of meteorites have got amino acids in them. They've got quite complex, they've got very complex carbon in them. They've got maybe 2-8% of something which is a real big network. The nearest explanation, or the nearest analogue on Earth is kerogen from oil shales. So you've got this huge, great big mat of mixed aromatic and aliphatic materials bridged together with nitrogen and oxygen and you know, the odd bit of sulfur and stuff like that. So you do have very, very complex organics in meteorites. So far, there is no sign at all that any of them were produced by biology.
But could they then produce biology?
Yeah, in as much as any organic material could, given the right circumstances, produce biology. Yeah.
I'll take one final question at the back there, and then I think we have to finish for the day.
Thank you as well. If I'm going to get at two things from your talk, one fairly early on and one right at the very end. The early people who we call scientists, who called themselves natural philosophers, certainly in the European tradition, gave the understanding that they were studying God's creation, which is where you, effectively where you ended. They were looking at what God had created.
Absolutely.
They weren't trying to disagree with what was there, they wanted to find out more about it.
Yeah.
How do you feel that fits into basically everything else that you said?
I think that you're absolutely right that the earliest scientists were doing things, you know, because there was an assumption that it was all created by God. And some people, you know, got into trouble for thinking that they could actually look at God's work and try and understand it. How that fits in with scientific progress, I don't know, since the Industrial Revolution, when we got more idea about designing scientific experiments, you know, Michael Faraday himself, of course. Most people. Oh, sorry, that's my timer. Stop. Most people would say, well, you know, I'm a scientist. I'm not trying to understand God. I'm not trying to understand God's creation. I'm trying to understand, you know, what the fluvial history of Mars is. So I think, by and large, most scientists don't. But they've all got this impetus, this incentive. They want to explore. They want to find the answer. And I don't think that impetus is any shallower or stronger than it was with the earliest scientists. I think we all have that inbuilt in us, the urge to want to know and to explore. You see it, you know, I've got a grandson who's 9 months old, he's going from crawling to walking, and you can see his determination. He is going to stand up. And now he's got a tooth, he's going to stand up and bite you. So, you know, you can see it right from that early stage, you know, wanting to push forward.
On that, I think we'll finish for the day. We've been treated to a very engaging and wide-ranging talk today, so can you join me in thanking you?